Okay. First, let me share my screen first. Um, okay. So whether my PPT is visible? Yes.
Yes, sir. Yes, sir.
Okay. Thank you. So in the last class, we started off with our first module, that is soil exploration. Okay. So in that soil exploration, we already covered quite a bit of portion. Okay. So what we wait a minute. Where is this? Yeah, cursor highlighter. Okay. Okay, so we started with the introduction. Then we have seen objectives and importance of the soil exploration. Wait a minute. Yeah. So, uh, so we have seen the objectives and importance of the soil exploration, and also we have seen different stages of the soil exploration. Okay, so what are the different stages? First one is the preliminary investigation, and another one is the uh, detailed investigation. Okay, so in the preliminary investigation, what we have seen, preliminary investigation means topology and what is the nature of soil, or you can study some topographic or aerial survey also you can do. Okay, so in a nutshell, it is called as a desk study. Okay, so with that desk study, what you can do, you will, roughly you will get some idea about the site. Okay, so once you get that idea, then you can prepare for the, you can plan for the detailed investigation, like what kind of boring system is suitable for that particular strata, or what kind of in situ test should be done, what kind of what kind of sample should be collected. Okay, so those things, everything we can plan it from the preliminary investigation. Okay, so even preliminary investigation includes the geophysical tests. Okay, so then we will, in the detailed survey or detailed investigation, we will have some boreholes. Okay, so we will have some boreholes, and then we will collect some disturbed and undisturbed soil samples with the help of some samplers, and also we will carry out some laboratory and field tests. Okay, then we also seen stabilization of the borehole. Okay, so once you drill the borehole, how you can stabilize. Okay, so because if at all while in the borehole, if at all if you encounter with some weak soil, the wall of those boreholes will collapse. Okay, so to avoid that collapse of the borehole wall, you have to stabilize the boreholes with the help of, maybe you simply use the water, or you can use some bentonite slurry, or you can use some casing pipes. Okay, then sampling technique we have seen. Okay, so sampling techniques means there are two types of samples. Huh? What are those samples? If just a minute, I will get this one note and then. Okay. Okay, so there are two types of sampling methods. One is disturbed soil samples. Disturbed soil sample. Another one is the undisturbed soil sample. Undisturbed soil sample. Okay. When you call as a sample as a disturbed soil sample, if the particle arrangement of the, or if the solid particle arrangement of soil is disturbed while sampling. Okay, while sampling, then it is called as disturbed soil sample. Disturbed soil sample. Okay, so this white screen is visible now for all of you. Anybody can respond whether whatever I am writing, is it visible for you?
Sir.
Yes, sir.
Yes.
Yes,
Okay.
sir.
Okay. Thank you. So, so disturbed soil sample, when you will call as a sample as a disturbed soil sample, if the solid particle arrangement of the soil is disturbed while sampling, then it is called as disturbed soil sample. Okay. So if at all, if you are not, if you can able to preserve that whatever arrangement of the solid particles are there, no, if you were able to preserve while sampling, then those are called as undisturbed soil samples. Okay. So again, to get these disturbed soil sample or undisturbed soil sample, we need what? We need samplers. Okay, so we need a samplers. Again, in the samplers, there are different types of samplers are there, like a thin wall sample, thin wall sampler, thin wall sampler. It is also called as a Shelby sampler. Okay, so it can also be called as Shelby sampler. And also another type of sampler is a split spoon sampler. Split spoon sampler. Okay, so with the help of these samplers, what we'll do, we'll take samples. That sample may be a disturbed sample or it may be a undisturbed sample. Okay. So until that we have discussed. So we'll so disturbed sample or undisturbed sample. Disturbed means the arrangement of the particle is disturbed here. That's why it's called as a disturbed sample. But undisturbed sample means arrangement of the particles are preserved here, right? So whatever a particle arrangement is there, that you have preserved here. That's why it's called as undisturbed sample. So this is called as a block samples. Block sample. And these are called as tubular sampler. Tubular sample. Okay. Again, in the disturbed sample, we have two types. Okay, so again in the disturbed sample, we have two types. One is representative sample. And another one is non-representative sample. Okay, so we'll see when you will call when you can call a disturbed sample as a representative or non-representative sample. That also we'll see here. Okay, so representative sample means if you are able to maintain the proportion of mineral constituent, then they are called as representative samples. If you are not able to maintain that mineral constituents, then you can call it as a non-representative sample. Best example for non-representative sample means, see, if it is a ground level, this is the layer 1. This is layer 1 and this is layer 2. When you are collecting the soil sample, when you are collecting a soil sample, if you could able to like the soil particles of layer 1 and the soil particles of layer 2 are mixed up. Okay, so then those kinds of samples are called as non-representative samples. While sampling, if you can able to preserve whatever layer 1 soil particles are there, no, if you can able to preserve that constituent materials of layer 1 separately and layer 2 separately, then those are called as representative samples. Those are called as non-representative samples. Okay. And we have seen some features of the soil samples, that is disturbed structure. What will be the features of the disturbed soil sample? Those things we have already seen. And also we have seen the undisturbed soil samples, and their features also we have seen in the previous class. Okay, so now coming to the actual syllabus of today's class. Okay, so today I am planning to cover different sampling tools. Okay, so these are the sampling tools. A sampling tool look something like this. Okay, so here it's this is the sample tube. Okay, and this is the cutting shoe. Okay, so this is the sample tube. Sample tube will be like this, and there will be some cutting shoe will be there here. Okay. So something like this it will be there. Okay, so to take undisturbed samples from the borehole, a properly designed sampling tools are required. Okay, so these differ for cohesive and non-cohesive soils. Okay, so ideally there is no undisturbed soil sample. Okay, so truly speaking, in some or other way we will be disturbing the soil sample while collecting the while collecting the soil samples. Okay, so there is no 100% undisturbed soil samples, but you can like based on the certain parameters, you can tell that a soil sample is to some extent it is a undisturbed soil samples. Okay, so what are those parameters? So first parameter is the area ratio. Based on the area ratio also I can tell whether whatever collected soil sample is disturbed or undisturbed soil sample. Okay, so if you take the area ratio, if you calculate the area ratio, and if it is less than 10%, then sample is considered to be undisturbed soil sample. Okay, so what is area ratio? So area ratio is nothing but dw square. What is the dw? Dw is nothing but the outer dimension of your cutting shoe minus the inner dimension of your cutting shoe. Square of those, difference of square of those divided by the dc square. That is again the inner dimension of your cutting shoe. dw square minus dc square divided by dc square is called as area ratio. So what is dw? dw is the outer diameter of your cutting shoe, and dc is the inner diameter of your cutting shoe. Okay, so this term is so yeah. Here I am telling what are those parameters. dt, what is dt? dt is nothing but you see, this is the dt. dt is this one. What is dt? Dt is nothing but outer diameter of your sampling tube. Sampling tube outside diameter, and ds is the inside diameter of the sampling tube. dw is the outside diameter of your cutting shoe, and dc is the inside diameter of your cutting shoe. Okay. So this is the area ratio definition. Okay. So similarly, based on the area ratio, how we can tell if your whatever area ratio is, if at all the area ratio is less than 10%, then that soil can be classified, or that sample can be classified as a undisturbed soil samples. Okay, so similarly there are another two definitions. So based on those definitions also, we can classify the soil as a disturbed or undisturbed soil samples. Okay, so first one is inside clearance. What do you mean by inside clearance? So the internal diameter of the cutting edge should be less than the outside diameter of the tube. Okay, that means if you see this one, inside, I'm talking about inside clearance. Okay, so inside clearance means you always deals with the inner dimensions of your cutting shoe and of your sampling tube. Okay, so this is the sampling tube. Sampling tube, and this is cutting shoe. So inside clearance means it is the whatever you see, this inside dimension is there. This one. Let me take this. This is DC. Okay, so this is DC. So this the inside diameter of your cutting shoe will be lesser than the inside diameter of your tube. Okay, you see this is the tube. Tube diameter is a little bit higher than your inside diameter of your cutting shoe. Okay, so the ratio of that will give me the inside clearance. Okay, so inside clearance is nothing but your ds minus dc divided by dc. Okay, so this dimension ds minus dc. So ds minus dc divided by dc will give me the inside clearance. So why we have to provide this? Why we have to make the dimension of your sampling tube slightly higher than the dimension of your cutting shoe? Any guess why we have to do like this? Because see, once you penetrate this sampler inside the ground, what will happen? The soil will be cut. Okay, so the soil sample, let me erase this, then it will be more clear for you. Okay, see, once we drive this sampler inside the ground now, what will happen? This much we'll have a soil sample like this, right? This is soil sample. Soil sample. See, little bit we are providing some space here between your inside diameter of your sample tube and your sample itself, because so once the soil sample enter inside the tube, no, then it is having some tendency to expand. Okay, to accommodate that expansion, we are providing some clearance here. Okay, that's why it's called as an inside clearance. Understood? No, why it is called as inside clearance? What is the significance of this inside clearance? To allow the soil samples to accommodate whatever expansion will happen. To accommodate that expansion, we are providing some space here. That is called as inside clearance. So inside clearance Ci is equal to ds minus dc divided by dc. Similarly, there is another clearance that is called as outside clearance. Okay, so what is the outside clearance? Outside clearance means always you will deal with the outside dimension of your cutting shoe and outside dimension of your sampling tube. Okay, so that is nothing but dw so this dw minus dt, dw minus dt divided by dt. Okay, so will give me the outside clearance. See, so the outside clearance means the outer dimension of your cutting shoe is bigger than the outer dimension of your sampling tube. This is the outside diameter of your sampling tube is little lesser than the outside diameter of your cutting shoe. Why we have to provide this outside clearance? Because see, while withdrawing this sampler from the ground, what will happen? You will get a resistance only up to this level. Okay, so only this much length of the cutting shoe will offer the resistance, because this much length of your sampling tube will be away from your ground surfaces, so it will offer less resistance while pulling off the sampler. Okay, so that's why we have to provide outside clearance. So now you understood now the significance of the inside clearance and significance of the outside clearance. So what is the significance of inside clearance? To accommodate any soil expansion of the soil sample. To accommodate that soil expansion, we will provide some inside clearance. Okay, so why we will provide outside clearance? Outside clearance will be given because it will offer lesser resistance while lifting off. Okay, so that's why we have to provide some outside clearance. Okay, so based on the percentage of your inside clearance and outside clearance also, we can classify the soil. We can classify the sample as a disturbed or undisturbed soil samples. Okay, so those things there we will see we will take one problem. Okay, so in that problem, that is a examination problem only. In the examination they will give you these dimensions. Okay, so dc, dw, ds, dt, all these dimensions they will give you, and they will ask you to find out whether whatever soil sample will be collected from these sampler is a disturbed one or it's an undisturbed soil sample. They will ask you. Okay, so same problem I will try to solve it. Then at that time it will be more clearer for you. So there is another ratio called as recovery ratio. Okay, so this recovery ratio also is a very important parameter to decide whether the soil sample is a disturbed one or an undisturbed one. Okay. So what is the recovery ratio? Recovery ratio is nothing but recovered length of sample to the penetration length of the sampler. So that means, see, this is the, suppose this is the penetration length of the sampler. Just a minute, I will erase all these doodle work. Yeah. So what is the recovery ratio? Recovery ratio is nothing but this is the penetrated length, total penetrated length. Divided by the length of the soil sample inside. Okay, so you would have got a soil sample up to this much. This is soil. This is the length of soil sample, and this is the penetrated length. So if you would have penetrated this much length, then whatever soil sample you have got in that, this is the length. Okay, so the ratio of those will give me the recovery ratio. So what is the recovery ratio? Recovery ratio is nothing but recovered length of sample to the penetration length of sampler. That means if you have a recovery ratio of 1, that means whatever length of penetration is there, the same amount of sample you have got. Okay, so that is called as a good recovery. Okay, so that is called as a good recovery. If your recovery ratio is less than 1, then that indicates you are getting a compressed soil sample. If your recovery ratio is greater than 1, that indicates soil is swelled. Okay, so depending on your recovery ratio also, you can classify the soil as disturbed or undisturbed. Okay, when you call as a undisturbed, if your recovery ratio is equal to 1, then you can call it as undisturbed. If your recovery ratio is not equal to 1, then you can call it as a disturbed soil sample. Understood, no? Okay, there are some notes here. What are those notes? See, soil samples are required for lab test. Okay, so why we have to do all these? Uh, why we have to collect the soil sample in first place? Because to test them in the laboratory. Okay, so we have to do some laboratory test. Okay, so the whatever results we will get in the laboratory, those depends on the quality of the sample we are obtaining at the lab. Okay, so if the quality of sample is very poor, then obviously you will get a very poor results. If the quality of sample is very good, then obviously we will get a very good quality of results. Okay, so always it will be very difficult to collect the undisturbed soil samples for sands. Okay, so like non-cohesive soil, non-cohesive soil. Okay, so like a sand and silt. Okay, so it is very always difficult to get these non-cohesive soil undisturbed soil samples. Okay, so it is always difficult to get the undisturbed soil samples for sand and silt. Okay, so then obviously whatever laboratory test we will do on these sand and silt, they are of doubtful, because the sample quality itself is the doubtful. So this kind of, that's why we always rely on the field test. Okay, so those are called in situ test. So for sand and silt, we will rely on field tests. Okay, for cohesive soil, for cohesive soils, it is little bit easier to get the undisturbed soil sample. For cohesive soil, it is easier to get the undisturbed soil samples. Okay, so once the quality of the samples are very good, then obviously we can rely on those laboratory tests. Okay, so wherever you obtain the cohesive soil, wherever you encounter cohesive soil, then you will get the undisturbed soil samples, and and then whatever lab tests will be performed on those undisturbed soil samples, obviously of a good quality. Okay. Okay, so this is the problem I was talking. Okay, so this is some examination problem. Okay, so what they given, so this figure they won't give. Okay, so I given this figure just to convey the for the demonstration purpose. So what they are telling, determine the area ratio, inside clearance, outside clearance for the given sampler tube, and comment on the nature of the sample obtained from the sampler. Okay, so they are asking you to comment on the what kind of sample you can able to get from these sampler. Okay, so what is the outside diameter? Outside diameter is 165 mm. Inside diameter is 150. Both are of a cutter, and outside diameter of the sample tube is 161 mm, and inside diameter of the sampler tube is 156 mm. Okay, so you have to remember those formulas to calculate area ratio, inside clearance, outside clearance. Okay, so now the area ratio is nothing but dw square minus dc square divided by dc square. So dw square minus dc square divided by dc square. 165 minus 150 square divided by 150 square. Okay, so I got around 21%. So 21% means it is higher than 10%. Then higher than 10%, because say to comment on the quality of the sample, if it is more than 10% means it is a disturbed soil sample. Okay, so whatever sample you will get from this kind of a sampler is of a disturbed in nature. Then we can calculate the inside clearance. So inside clearance CI is nothing but ds minus dc divided by dc. How much I got? 4%. Okay. And what is the outside clearance? Outside clearance is I got around 2.48%, approximately 2.5%. So obviously they are more than 3% and more than 2%. That's why it is called as, hence the sample will be a disturbed soil sample. Okay. So now you understand now how I can tell just based on the area ratio or inside clearance or outside clearance or even for a recovery length also. Based on those things, I can classify the soil as a disturbed or undisturbed soil samples. Okay, so there are some videos I have put. These are some YouTube link. Okay, so you please go through these YouTube link. So you will see some drilling and sampling techniques. Okay, so and also anyway, I will upload some videos also in the Google Classroom. Okay, in that also you will find these videos. Okay, so you can download them and you can watch them on your at your free time. Okay, so any doubt till now before going into the next topic? No? Any doubts are there? Huh? Any doubts are there, please?
No, sir.
No. Sandeep backward. Any doubts? Sandeep, are you there? Okay. See, you can unmute yourself and you can straight away talk to me. Okay, so no need to message. Priyadarshini, are you there? Priyadarshini. So if you have any doubts, please ask me. Sagar.
No, sir.
No. Okay. So shall I continue?
Yes, sir.
Okay. Thank you. Yeah. Now we'll see some geophysical tests. Okay. So till now, what we did there? Till now we covered objectives of the site investigation, then some boring methods, and type of samples and type of samplers also. Sample and sampler. There is some slight difference. Okay, so while I am pronouncing, be careful. Okay, whether I am telling sample or a sampler. Sampler is an equipment with which you will collect the sample. Understood, no? Okay, now coming to the geophysical exploration. Okay, so geophysical exploration is nothing but without drilling any borehole, without drilling any borehole inside the ground, I can find out what is the different layers of the soil. Of course, there are some other geophysical tests are there. So even those some geophysical tests are there. Those can be performed inside the borehole. Okay, so and some other geophysical tests are there. Those can be performed only at the ground surface. Okay, so at the ground surface, if you can do those geophysical tests, then I can estimate what are the different layers are there. Okay, so suppose this is layer 1. And this is this is layer 1, and this is layer 2, and this is layer 3. This kind of layers I can find out just by performing some geophysical test at the ground surface. So the subsurface soil or rock stratum without disturbing the ground much. Okay, so we can obtain subsurface soil or a rock stratum without disturbing any ground. Okay, so because we are not at all drilling any borehole or we are not at all disturbing any soil samples inside the ground, without doing boreholes only, we can get the layer sequence of these soil strata. So geophysical methods are indirect surveying technique. Okay, so they are called as indirect surveying technique. Why it is called as indirect surveying technique? Because we are measuring some parameters on the ground surface, From that parameters, I can estimate a different soil layers. What are those parameters? We'll come to that in the coming slides. So geophysical methods are indirect surveying technique based on measurement carried out on the ground surface or in the hole. Hence, they are quick and less expensive compared to conventional bore log investigation. Okay, so they are very less expensive. Why it is less expensive? Because we are not going to drill any boreholes here. Okay, so because drilling borehole is a very costly affair. So just to give some number, see, if you want to drill one borehole, if you want to drill, so there will be two types of cost. One will be the mobilization cost, and another one will be the drilling cost. Okay, so mobilization cost means suppose if you want to drill a borehole in the Bijapur, so but in the Bijapur there are no borehole drillers. You have to hire from some other cities, like maybe from Hubli or from Bangalore. You have to hire them. So they will ask you to give some mobilization cost. Mobilization cost. Okay, that mobilization cost will be vary from city to city. Like if you want to hire from Bangalore, then they will ask you to give just 1 lakh rupees. 1, 2, 3, 4, 5. Yeah, 1 lakh for just for the mobilization cost. Then for 1 meter run, if you have a soil, if you have a soft soil, then cost will be around 1,000 rupees, 1,000 to 1,500. Even up to 1,900 also they will charge. If you have a soil. Then if you have a rock, then they will charge you for 1 meter. They will charge you for 1 meter anything around 2,500 to 4,500. Understood, no? See, this is the cost of the drilling a borehole. Suppose if you have 10 boreholes, and if you are drilling for 6 meters in each borehole, then the cost the cost will comes around 5 to 6 lakh. That much it will cost for the boreholes, right? So to avoid this much money, what you can do, you can go for some geophysical exploration. Okay, so this geophysical exploration means we are not anyway the mobilization cost will be very less, because very simple equipments will be there to carry those equipments. Mobilization cost will be very less. Maybe around if you give like 5,000 to 6,000 rupees, within that much amount of money they can come to your site and they can perform the test. Of course, the test cost also will vary depending on the company. Okay, so but compared to the drilling a borehole, the geophysical tests are very cheap. Okay. Okay, the role of geophysical method is twofold. What is the role? First, evaluation of geotechnical boundaries to model the subsoil condition, and evaluation of the physical and mechanical parameters. Okay, so first, the main aim of the geophysical test is it will tell you roughly. It will tell you roughly what is the depth of each soil layers. Maybe this may be around some 2 meter depth. This may be around some 5 meter depth. This may be around some 10 meter depth. Like that, it will give some rough idea. Okay, so geophysical exploration will not give you accurate layers, but roughly it will tell you what will be the boundaries, and also it will tell you roughly the depth of the bedrock. Suppose this is the bedrock level. Bedrock level, it will tell you roughly the depth of your bedrock level. So this is the main or objective or role of a geophysical method. First one is it will tell you roughly the thickness of each layers, and also it will tell you the depth of the bedrock. Okay, now we'll see there are many geophysical tests are there, but in your syllabus only 2 geophysical tests are there. Those 2 geophysical tests only I will discuss. The first one is the seismic refraction method. The first method is called as seismic refraction method. So the aim of the seismic refraction test is to find out the thickness of soil layer and depth of the bedrock. The main aim is to find out thickness of soil layer and depth of the bedrock. Based on the fact that the seismic wave travel with a different velocity in a different layers. Okay, so what is the fundamental funda behind this seismic refraction is depending on the layer constituent materials of the soil layer, the velocity will differ. Okay, so the velocity of the waves, whatever waves you will create, they will differ depending on the density of your soil layers. Okay, or constituent materials of the soil layer. So what is the procedure? Procedure is something like this. Okay, so here we will put some geophones. We will put here D1, D2, D3, D4, D5, D6, D7, D8. Okay, so like this, some geophones will be there. Okay, so these geophones we will put here. So we'll at a certain interval time. Okay, so maybe the depth will vary. Okay, so sorry, the distance between the each geophone. Okay, so we'll put some array of geophones, and then here with the hammer we'll hit with the hammer here. Okay, so that by hitting with hammer, what I am doing, I am creating some waves here. Okay, so I am creating some waves, and here some geophones I have put in. Okay, so those geophones will record the time of arrival of these waves. Okay, so maybe some T0, T1, T2, T3, T4, like that. So they will record the time of arrival of these waves. How these waves are created? Just by hitting some hammer on the ground. Okay, what is the procedure here? You see, first let me erase this one. First, what we are doing, we are creating some shock waves are generated at point A by detonation or some impact. If you are placing geophones with a very big or with a very huge distance, then you can have some detonation, a small small crackers or some small blasting can be done here. Or if blasting cannot be done, or you can hit with some hammer. With hammer you can hit it here, so that you are creating some shock waves. So those shock waves will be picked up by these geophones. So the arrival time of first wave at each geophone is recorded. Okay, so arrival time is recorded at each geophones. Then once you record that, you plot them. You plot that time of first wave arrival versus the distance between those geophones. You plot a graph between the distance between geophones and the time of first arrival. Okay, so like that, once you plot that graph, you will get a straight line like this. Okay, so this is one layer, and this is another straight line, and this is another straight line. Okay, so there are 3 straight lines you will get here. So the slope of these straight lines, will give you the velocity of those shear waves in those layers. Okay, see, you are getting 3 different slopes here. Okay, so this is slope 1, this is slope 2, this is slope 3. That means you have a 3 layers of soil. Okay, so this is first layer, second layer, and this is third layer. Okay, so if you are getting only two slope, then that means you are having only two types of soil layers. Okay, so if you are getting three slopes, then that means, that indicates you have a 3 layers of soils before reaching the bedrock. Then the slope of AB, BC represent the seismic wave velocity in the upper and middle soil layers. From the slopes of line CD, the velocity wave in the rock strata can be obtained. Okay, so this slope is there, no? This slope is nothing but corresponds to the velocity in the third soil layer. This is the third soil layer. This is layer 3. This is layer 1, and this is layer 2. 1, 2, 3. Okay, the slope of this portion is nothing but the velocity of those shear wave in the layer 1. Okay, the slope of this portion will give me the velocity in the second layer. The slope of this portion will give me the velocity in the third layer. Okay, so what is my third layer? My third layer is the bedrock. That means the shear wave velocity in the bedrock is very high as compared to your soil. Okay, like that I can determine different layers of soil just by looking at the this graph. That graph is nothing but the time of the first arrival of the shock wave versus the distance between those geophones. Okay, and now see, by looking at this graph, I can tell there are 3 layers of soil, but I cannot tell what is the depth of those layers. To tell you the depth of those layers, then I should use this formula. So H1 is nothing but D1 by 2 into square root of V2 minus V1 divided by V2 plus V1, and H2 is nothing but 0.85 times H1 plus D2 by 2 into square root of V3 minus V2 divided by V3 plus V2. Okay, so if you use this formula, then I can find out the depth of the each soil layers. Okay. So this is another picture of the same figure. Okay, you see whatever this figure I shown, no? So this is the another way of representing the figure here. See, this is the geophone. Okay, so this is the hammer. With the hammer, if you hit with this hammer, what will happen? Waves will be created. The waves will be created, and the time of arrival it will record the time of arrival. Okay, T0, T1, like that. Many geophones will be there. So this is another another way of representing the same figure. Okay, so either you can draw this figure, or you can draw this figure also. Whichever, just to convey the message effectively, I am putting these figures. Okay, so now see, each soil layers will have the different velocity. Okay, so suppose if you are getting from this slope, if you are getting the velocity is somewhere around 180 to 365 meter per second, then the first layer you can call it the first layer may be sandy type of soil. Okay, so if you are getting the velocity in the range of 365 to 580, then you can call it that layer as a sandy clay. Okay? If you are getting the velocity somewhere in the 3050 to 6100 meter per second, then you can call that layer as a granite, like sandstone, gravel. If you have a gravel, then the velocity you will get in the range of 490 to 790 meter per second. Okay, so this table is taken from this IS 1892. In the IS 1892, if you refer, they have given what will be the typical shear wave velocity in different soil layers. Suppose if you have a soil layer of a sandy clay, then you should get a velocity in the range of 365 to 580 meter per second. Okay, understood? No? Any doubts here regarding seismic refraction method? Any doubt regarding seismic refraction method? Bhagyashree? No. Akash Nayak, any doubts are there? Akash, are you there? Akash Nayak? Regarding seismic refraction method? Or Nikita Nayak? Any doubts? No, sir. Okay. Varsha. Please feel free to ask any question. Okay, so I won't mind at all. Okay, so please, I rather encourage people to ask me questions. That question may be any question. Okay, so you may be thinking that may be a silly question, but for different people the perspective will be different. Right? So don't hesitate or don't shy away to ask any questions. The more you ask, the more you will learn. Vishal, any doubts? Vishal Chitragar. Okay, so shall I continue? So
Yes, sir.
Okay, so I will go to the next method of a geophysics. Okay, before going to the next method, there is one examination problem. See, whatever here we have discussed, no, based on that you can expect some problems. In the either they will ask you to write a procedure for this seismic refraction test, or they may ask a problem also. Okay, so anyway, the procedure, everything I given here. So now let us see some examination problem. So this is one examination problem. The following data were collected from the seismic refraction test in an area. Determine the depth of a first two strata from the ground level. Okay. So these are the distance for peg from the geophone. Okay, so at 10 meter, at every 5 meter interval, they put geophones up to 30 meter, and then up to from the 30 meter at every 100 meter or 200 meter they are kept the geophones. Okay, and also they are given the first arrival time. Okay, the time taken for the first wavefront to reach the geophone. That means at a 16.5 millisecond. These are all in millisecond. At 16.5, suppose I will draw roughly. I will draw a figure here. Okay, so here, this is the hammer. This is the hammer, and this is the ground. With this hammer, they are hitting here. Okay, so first geophone is somewhere here. This is second geophone, and this is third geophone, and this is fourth. How many are there? 1, 2, 3, 4, 5, 6, 7. 4, 5, 6, 7. Okay. So the distance for peg from the geophone. Okay. So at 10 meter, first geophone is there. At 15 meter, second geophone. At 20 meter, third geophone. At 30 meter, fourth. At 400 meter. And the time arrival. Okay. So at T1, 16.5. T1 is equal to 16.5 millisecond. T2 is equal to 25 millisecond, T3, T4, T5, T6, like that, and T7. Huh? They given all the data they given. Huh? Now what they are asking you to find out the determine the depth of the first two strata from the ground level. Okay, that means they in the problem itself they are telling there are two strata. Sorry. Okay, so this is ground level. This is layer 1. This is layer 2. In the problem itself, they are mentioning you first two strata. That means if you plot a graph, you will get two straight lines. Okay, one straight line will be like this, and another straight line will be like this. Understood? No? Let me erase this. Then I will draw one more figure here. Okay, so if you have a two layers, then this is first straight line, and this is second straight line. If you have three layers, then you will get one more straight line. This is layer 1, and this is layer 2, and this is layer 3. Okay, like this, 3 layers you will get. Since in the problem itself they've given you only 2 layers, and you restrict to only 2 layers. Okay. Now what I have to do? I have to plot a graph between. The distance versus time. If you can able to plot this graph, then I will get the two straight line, and then take the slope of those straight line. Take the slope of those straight line and inverse them. Then you will get the shear wave velocity in those layers, and then use those formula to find out the depth of each layer. This is H1 and this is H2. See, I already plotted a graph here. Okay, so this is the graph between distance versus time. So this is the first portion of the line. This is the first portion, and this is the second portion. You see how many points are 1, 2, 3, 4. 4 points here you will get, and here another 3 points you will get. Huh? You see, this is the first portion, and this is the second portion. If you can able to draw a graph between your distance and time, then I will get a first straight line, and then second straight line, and then take the slope of these straight lines. If you take the slope of these straight lines, I will get the shear wave velocity. So this is the V1 is the shear wave velocity in the first layer, and V2 is the shear wave velocity in the second layer. See, if you take the slope and inverse them, we will get see in the what is the shear wave velocity in the first straight line? 600 meters per second, and in the second layer around 4,000. Okay, so 6,000 means maybe around some first layer will be like a sandy type of soil. 4,000 means it may be some rocky type of soil. Bedrock you will get. 4,000 means always it's some bedrock. And the D1 is nothing but wherever they meet both straight lines, no, that is my D1. So this extend only 4 points will get, and then extend the straight line here, and then you extend the straight line from here. But wherever they meet, no, that is called as D1. So then use those formula to calculate the thickness of the soil layers. Okay, so H1 is D1 by 2, into square root of V2 minus V1 divided by V2 plus V1. Okay, so I know V1 and V2 I know, and also I know the D1, so that I will get the H1 here. This is my thickness of soil layer. Okay, so if I want to draw a figure, it will be something like this. Okay, so this is layer 1 and this is the layer 2. This is layer 2. The layer 2 is a bedrock. This is almost a bedrock here. How I can tell that it is a bedrock? Just by looking at the shear velocity. If I go to my previous slide here, 4,000. Where is my 4,000? It is in the range of this much. What kind of rock I am getting? Almost granite. And first layer, how much velocity I got? Around 600 meter per second I got in the first layer. Okay, so that means around 600. 600 means somewhere here like this. This one. So sandy clay. First layer will be sandy clay, and second layer will be your granite rock. Understood the problem? What you have to do? You have to plot a graph between this distance versus time. You plot a graph, and then once you plot a graph, you extend the straight line portion of the first line and the second line, and wherever they meet, that will be my D1. So once you get the D1, simply plug into that formula, so that I can find out the H1. Understood this problem? Any doubts are there in the problem? Whenever they give such kind of problem, first thing is you have to plot a graph. Once you plotted the graph, means half of the work is done. Only thing is you have to remember this formula and plug into that parameters and get the thickness of soil layers. Suppose if you have 3 layers, then there is another portion of the curve, another straight line portion will be there like this. Since you have only 2 layers, that's why we get only 2 straight lines are there. This is first straight line, this is second straight line. Suppose there are 3 layers, then we will get another straight line portion. Okay. So next method of geophysical test is the electrical resistivity method. Electrical resistivity method. What is electrical resistivity method? It is mainly used for groundwater exploration. Usually these geology persons are there. If you want to find out the water reserves to drill a borehole, usually they will use this test, this geophysical test. Even for the geotechnical purpose also you can use. Even for the geological purpose also you can use the this test. But mainly it has started from the geological point of view. This method depends on difference in electrical resistance of different soil layers. Okay, so here the main funda is the electrical resistance. Okay, so different soil layers will offer you different electrical resistance. In the similar way, in previous section also we have seen in the seismic refraction method, different soil layers will offer you different shear wave velocity. In the similar fashion, different soil layers will offer you different electrical resistance. So based on that, we can find out the different soil layers in the ground. So each soil has its own resistivity depending upon the water content. So how much water content is, that depending on that, the resistivity also will vary, and compaction and composition. Okay, So composition means what type of solid particles are there. Okay, whether you have more silica content solid particles are there, or whether you have more iron content solid particles are there, like that. Depending on those mineralogy, also your electrical resistivity will vary. Okay. So what is the procedure here? The procedure is simple. First, what you have to do, you drive 4 electrodes. These electrodes are nothing but some metal spikes will be there. This is first one, second one, third one, fourth one. Okay, so these 4 metal spikes will be there that you should drive inside the ground. Once you drive inside the ground, you take a connection from first and second, and then pass some current. Okay, so here battery means what? You will allow some current to pass through these 2 electrodes. Okay, so like this, some current will pass. Okay, once you allow the current to pass, then there will be some voltage difference or potential difference will be there. That difference you measure from this potentiometer, and you measure the how much current you are passing. Okay, from this millimeter. So from the millimeter you are measuring how much current is passing between outer 2 electrodes. Due to that current, what is the potential drop in the 3rd and 4th electrode, that you measure. Okay, so what you two parameters we are measuring here. One is current we are measuring, and also the potential drop also we are measuring here. So first, what is the procedure? Drive 4 electrodes into the ground at an equal distance. Okay, so the distance between each electrode is same. Then current I from the battery flows through the soil between the 2 outer electrodes, producing an electric field within the soil. Okay, so electric field will be produced here between these 2 electrodes. Then the potential drop E is then measured between 2 inner potential. Okay, so between these 2, we are measuring potential drop. The apparent resistivity is given by rho is equal to 2 pi d into E by I. E is the potential drop, I is the current passing. Okay, so only 2 parameters we are measuring here. In my previous case, what are the parameters I have to measure? I have to measure only one parameter there. What the arrival of the shear wave velocity in the each geophones. Anyway, distance is fixed. Okay, so but here we are measuring 2 parameters. One is the current we are measuring, and as well as the potential drop also we are measuring. So see, now I'm again from the IS 1892 I am taking this table. Depending on the resistivity, you can judge whether the soil is a clay or a limestone or a quartz or a rock salt or a granite. Depending on the resistivity, you can tell. Okay, so see, this is the battery. This battery, through this battery, current is passed between these 2 electrodes. This one electrode and this is another electrode, and we are measuring the potential drop between these 2 electrodes. Once you measure potential drop and the current, then use this formula and calculate the resistivity. Once you get the resistivity, you check with this table how much resistivity I am getting. Based on that, you can calculate what is the type of soil present below the ground. See, clays will offer you electrical resistivity in the range of 1 to 120 ohm meter. If you have a limestone or a quartz, then the resistivity will be in the range of 10 to the power of 12 to 10 to the power of 10 ohm meter. If you have a granite, then what is the resistivity? 5000 to 10 to the power of 6 ohm meter. Okay. Okay. So any doubts still now? No? Any doubts are there? Kiran Kumar Rathod, any doubts?
No, sir.
No. So this electrical resistivity method and seismic refraction method, they are very important. Okay, so either definitely there will be a one question. Either they ask you to write a procedure of a seismic refraction method, or they may ask you to solve a problem based on the seismic refraction method. Okay, and also there is a possibility of asking these even problem also can be asked from the resistivity method. Anyway, one problem I will solve based on resistivity method. I have already solved a problem on a seismic refraction method. Okay. So in the next class, what I will do, I will solve one problem on the resistivity method, and then there is a small portion at the end that is how to find out the water table from Worsley method. So this is another topic that I will cover in the next class. So if you have any doubt, I can take up some questions. So please ask if you have any doubts. So I will stop the recording here.